Okay, once slide forwards. So yeah, I was going to start to say that the 2018 drought, which is already the largest documented outbreak of European spruce bark beetles in Sweden. The total of estimated 17 million cubic meters of spruce trees being killed in southern Sweden in 2018 and 2020. And that's the study period of this specific study. And so also an estimate on larger scale that more than a quarter of Europe's current Norway spruce growing stock is potentially exposed to bark beetle outbreaks. And as said already before today, that it's the likelihood is high that during climate change, these risks will increase in future. And when you have these hot and dry summers, then you will have the drought stress imposed on the trees, but also kind of the term habitat suitability here, so the beetle activity on the other hand. But then kind of the local variation is also controlled by the environmental features or factors, as a synonym for it. And those together as being here as building up the risk in the local landscape level, and we'll be focusing on the environmental features here. And the specific research questions were that can you use geospatial data in random forest in unison to accurately classify stands that are predisposed to bark beetle attacks, and which environmental features were most important and how did they affect the predisposition of the stands to bark beetle outbreaks or attacks, and were there differences amongst these features during the drought year of 2018 and then the 2019 and 2020 period when there was the weather conditions were closer to the long-term average, but the population levels of the bark beetles were much higher. In the random forests, I can say that they were mainly chosen to the input data that we'll be talking here, the harvester machines, as all the data will be, or most of the training data comes from these harvester machines with these global navigation systems. They always map the XY coordinates of each site that they are on. But the problematic part here is that once you have these machines that have also detectors in a crane, so then you get actually individual coordinates for each tree. But some of them have only a receiver at the kind of on top of the harvester machine. And at those places, you might get multiple trees with the same XY coordinates. So the study area where this harvester data was available, it's 48,600 square kilometers in southeastern Sweden. And we split this into two study periods, 2018 and 2019 to 2020. And this led into a data set where we have places of infested or coordinates of infested trees for the 2018 year, over 24,000. And for these two upcoming years, then 75,000. But the problematics with using these harvester data sets aren't solely on that you might have duplicate coordinates, but also that it tells you only positions of the attack trees and you don't have any healthy training data sets. So we made some decisions how to move forwards with the pre-processing of the data. And for those harvester machines that have only the coordinates from the rooftop, we made this decision that we limited it to 10 trees. So those were still seen as kind of valid data points, as these red points within the forests. So the harvester might have stood still and harvested 10 trees around it. But sometimes you got also data points where there was tens and tens of trees with similar coordinates, and those were all discarded. And we had some inventory data, but it was very limited compared to these tens of thousands training points of the attack trees. So what we did is that we got an estate map or a property map, and this move relies on the assumption that forest owners, when they brought the harvester machines in, that to the economical purposes, they would have checked which areas needed to be harvested, that which are attacked. So rest of the trees would be healthy. And this leads into these green areas that you will see that were treated then as healthy stands. But then you will have much more healthy data than of these infested. And we use stratified sampling of the healthy data, where for the whole of study area, we calculated the coverage of soil types and forest types together as control variables to get a representative data set of the healthy data on the study area. Then for training, what are these environmental features? They are all derived from open geospatial datasets. So from elevation, digital elevation models, there are elevation aspects, slope, and so-called geomorphometry. So within the location within the local, or position within the local landscape. The forest type, there were monocultures of spruce, or then spruce and pine mixed, or then mixed forests. So there are spruce trees within deciduous forests. And from some of them, we then derived also these metrics based on distance. So how far it was from forest edge. Similarly, from clear-cut data set, how long distance to nearest clear-cut done during that year or 5 years before it, or then longer ago, 6 years to 10 years ago. And then also from the SOS digital forest map, mean canopy height and total spruce volume. So I can say that there were more predictors in the beginning, but they have been pruned before training these models due to collinearity purposes and of problems with collinearity. The data was split to 80% to training and 20% for validation. And the random forests, as we have, the datasets were classified as binary, so either healthy or attacked. But the models actually predict the probability of belonging into the class of being an attacked pixel. So then you get a continuous value of the probability of being attacked. And this can be seen as a quantified information of the risk variation within the landscape. And you can produce these risk maps. And with the drought year, the accuracy was 85%. And whilst you would add the predictors that include distance to infestation during or attack during the previous year, so that brings a little bit higher accuracy for the normal period. The colors aren't very vivid here, but otherwise you would see that the areas with the high risk already during the drought period, once there was infestation or attack at those areas, then you would see this cluster of very high values during the normal period because it calculates the distances to the previous year's infestations. But this gives you only a quantification of the risk and mapping areas that are within the risk, but doesn't really tell you why or what is happening within the landscape. So in 1950s already there was the original Shapley values were created for game theory. So you could evaluate, for instance, in sports games, what is the value of a player, how does they contribute for the team. But the Shapley values work in that sense that the zero of the Shapley value would be the average between the healthy and attacked classes, so 0.5. So all of the negative Shapley values tell that the model was pushing attack pixel, the predictions towards it being a healthy stand, and the positive ones are showing that it at that specific pixel, it was this attribute was telling that it's in higher risk. So you can summarize these over the whole study area, like seen on the left-hand side. And the mean absolute values were used to kind of tell the total importance of them, so the canopy height. But then you can also see that how it moved or behaved within the model. So the higher the kind of average canopy height was, the higher the risk, mainly. And for instance, for the soil wetness, that during the drought year, areas with the lowest soil wetness values were in highest risk. But then you can also choose these by area. You can subset by coordinates or by forest type that you want to look at. So here is a subset from the normal period model of the previous infestations. So the Euclidean distance to a tree that was attacked the last year. So then you see that if it's right in the next pixel, you get very high risk values just because of this one predator. And then it rapidly starts decreasing. And after 250 to 500 meters, you're starting to kind of lose the impact of this distance to previous infestation as a valuable predictor for the risk. But then you can also compile these in any way you want to look at them. So here on left-hand side, there's a kind of forest type, that pure spruce forest, mixed coniferous and mixed trees, and volume and canopy height put all into one plot. So when you go over the 0 limit of SHAP values, the positive values are increasing the risk within the landscape. So it's not perfectly visualized in this one, but the slope of the risk increasing is higher in the pure spruce stand than it's, for instance, in the mixed one. And on the right-hand side, there's a summary of how looking at the position within the landscape. So same as in, for instance, the poly presentation. So when there isn't a high gradient of or the difference between the elevation in the whole study area, so then more of the kind of positioning within the local landscape. So if the areas that were up on the hills and had rocky and blocky soils, for instance, they were usually defined as the areas in the highest risk. And this would also give implications that, for instance, landowners could subset their own forest stands, and you can see how these variables actually change within your forest stand. So as a summary of these, increased infestation risk could be identified with good accuracy. But also the information on the importance, but the dynamics of the features can be derived, when usually people only derive how important the variable was, not how it behaved. And this could help to also make threshold levels kind of on these variables. So when you meet these criteria, it's easier to focus on areas where the mapping of these damages should be done. The risk was increased both in spruce and mixed coniferous stands, much more than where the mixed forest mainly decreased the infestation risk. And for the drought year, I didn't speak so much on the differences here, but the stands with high average canopy height that were located high on the local landscape and had low average soil moisture were in greatest risk. But the average canopy height actually was, in total, it had a lower importance during the drought, which was kind of showing that younger trees were also attacked during the drought. And looking at the workflow, I won't go through all of it, but inputs from the harvester datasets and inventory data and geodata, they went into these rasters with 10-meter pixel size, split into two models. Here I won't be presenting the feature selection because that's just limiting collinearity between the variables. But I want to say that once the models were trained and these SHAP values are calculated, you can get the local importance on pixel level, which will help to find these feature dynamics or look at the global importance. So how important was the variable in the landscape. But thing to note here is that the limitation is that the model is global, even though you get pixel-wise values of importance. So it doesn't, for instance, take into account latitude. So if you would use it in the even larger areas, then there are kind of parameters that haven't been included here. And the limitations in our training data, so if it would be possible to get data sets which include also the healthy tree smart kind of, it would make this much more robust in a way that we kind of build just workarounds for the data. And that also touches upon if you would want this to be annually updated, that either you have to have a constant flow of harvester data coming in, or use then satellite remote sensing or other possibilities to update kind of where the newer attacks are happening in the future. And for that, I will say thank you. And if you want to see any specifics on the study, you can scan the new QR code home, and that will take you to the publication.